My paper for this year is based on the paper that I wrote for Bridges 2014, and that in turn is based on some of my earlier work. So let me take you back to where all of this started for me. In the early 2000s, I saw this mug that had been designed by David LaHavie and then made out of pottery, handmade, glazed, and fired by Tamar Ziegler, both of whom were mathematicians. And it was really cool. I wanted one for myself, but I don't make pottery. So what I did was I found a paint your own pottery place, and there they will provide you with a commercial mug that you can glaze and they will fire for you. And with a little bit of playing around, I was able to reproduce what LaHavie and Ziegler had done with their design. So what's special about this? Well, you'll see that this mug has 7 colors, if you count the white, which I do. And in fact, it turns out that each of the 7 colors touches all of the others. You might want to pause this, take a moment to check that. You really do need all the different views. But each of the 7 colors touches all of the others. And the reason why this is interesting is because this is something that you can really only do on a surface that has a hole passing through it. In particular, this is part of the 7-color theorem. So the 7-color theorem says that any map that's drawn on a torus, so that's like the surface of a donut or the surface of a coffee cup with a single handle, any such map can be colored with 7 colors so that no adjacent countries are the same color, which is not actually the surprising part. 7 colors is a lot, so sure, that seems reasonable. The interesting part is there actually exist maps that require all 7 colors. So that's sharp. You need up to 7 colors to color a map on a torus. And this is particularly surprising if you happen to know the 4-color theorem, because the 4-color theorem says that if you have a conventional map, say on a piece of paper or on a globe, you can always color in the countries with at most 4 colors so that no neighboring countries are the same color. But if you go up to a surface with a hole passing through it, the surface of a torus, then you may need as many as 7. So there are various ways to see this. One is the coffee cup. There's also a nice systematic way that you can see this using some geometry in the plane. So if you start with a tiling of the plane by regular hexagons, and you take 7 of those hexagons in a cluster like the one drawn here, and color them in with 7 different colors, then you can take this cluster of 7 hexagons and tile with them. So here's a few more copies of it tiled around, and if you keep on going in this pattern, you can fill the entire plane in this way with a regular design. In particular, this design repeats in a number of different directions. It repeats in this direction, and it also repeats in this direction. And what that allows you to do is to pick out a parallelogram that acts as a fundamental region for this design. So you could take this parallelogram, tile the plane with it, and it will give you the entire plane filled with your hexagon coloring, right? But what this also means is you can take this parallelogram on its own, and if you glue the left edge to the right edge and the bottom edge to the top edge, what you will end up with is a torus. And because of the way that the pattern repeats over and over again, the hexagons will flow smoothly over the torus. So you now have a torus that's covered with 7 hexagons, each of which touches all of the others. So there's your illustration that maps exist that require 7 colors. So the Paint Your Own Pottery place also had these little tea for 1 sets that consisted of a tea mug with a little teapot stacked into it. So when these were stacked together, you had 2 handles. And a surface with 2 handles, well, that's a surface with 2 holes through it. That's a 2-hole torus or a double torus. So the obvious next thing to try was to illustrate the corresponding theorem there, which is the 8-color theorem. It turns out that maps on double tori require up to 8 colors. But this was easier said than done. Because at that point, the only 8-color maps that I'd seen on double tori were these maps that were made by Sarah Marie Belcastro and Carolyn Yakel. And these were based on the pattern for hyperbolic baby pants from the first of the 3 collections of mathematical fiber arts that they edited, Making Mathematics with Needlework. So this was a chapter that they wrote together for this book that gave this pattern that allowed you to knit a negatively curved surface that then naturally sewed together into a pair of baby pants like the one that you see here. But those baby pants, because of the underlying math, naturally can be glued together if you attach the bottoms of the legs to the waist in the right way to make a double torus. And so this pair of baby pants by Carolyn Yakel is divided into 8 different colored regions, and if you glue it together in the appropriate way, you end up with an 8-color map. Now, I believe that Carolyn actually went second. I think Sarah Marie made her map first. Not positive of that, but this is Sarah Marie's map, and this is shown in the double torus configuration, but it's a little bit hard to see what's going on because it's, sort of twisted up in a kind of tricky way. And that's great. The problem is that these maps were designed a little bit ad hoc and definitely for this way of making a double torus, which looks completely different from the T-set. And I kind of didn't want to do something ad hoc. So I was hoping to find a framework that would give me a kind of symmetric, aesthetically pleasing 8-color map on a double torus. And in order to get to this, I started with the tiling of hexagons, right? So you'll remember you can get this torus by taking 7 hexagons and gluing them together in the right way. Here are the 7 hexagons, and the colors around the outside are showing how they're glued. This is taking the torus and dividing it up into a bunch of hexagonal regions. And so you have hexagonal faces and edges and vertices. You can do an Euler characteristic calculation. And that's instructive. So in this case, we have 7 hexagons. That's going to give us 7 faces. How many edges do we have? Well, the 7 hexagons have 6 edges each, so that's a total of 42 edges. But of course, we're overcounting because each edge has 2 hexagons glued together along it. We've double counted the edges. So if we take that initial 42 and divide it by 2, we find there are 21 edges in our torus. Right? And similarly for the vertices, we have 3 hexagons around each vertex. So each vertex from the original 42 is triple counted. The total number of vertices is going to be 42 divided by 3, which is 14. And if we fit these together, we find that the Euler characteristic chi, vertices minus edges plus faces, is equal to 0. And this is good news because chi is 2 minus 2 times the genus. So an Euler characteristic of 0 corresponds to genus 1, which means there's one hole through this, so we have a torus, as expected. Now, if we want to get an 8-color map, well, first of all, now each color has to touch the 7 other colors. So we're no longer going to have hexagons, we're going to have heptagons with 7 edges each. And now we can do the same sort of count. We can start it at least. We have 8 heptagons, so that's 8 faces. The total number of edges is going to be 8 times 7, and then we have to divide by 2 because each edge is in 2 faces, and we find that there are 28 edges. And that's as much as we can compute without knowing how the heptagons are fit together because we don't know how many are around each corner. But we know what genus we're aiming for. We're aiming for genus 2. And 2 minus 2 times the genus, in this case, is -2. So we want chi to be -2. We can put in the 8 and the 28 that we know already and solve for v, the number of vertices, and we find that v is 18. And this is interesting because the total number of vertices that we have to start with, counting them all separately before they're glued together, is 56. If we glued everything together 3 to a corner and we had 18 vertices, that would mean we were starting with 54 vertices. So we've kind of got 2 extra to burn up. And the most symmetric way to do this is to have 2 vertices that have 4 heptagons around them. And we have a total of 8 heptagons, so that's kind of perfect. The most symmetric way that we could do this is to take 2 clusters of 4 heptagons each, right, and put them all, each cluster around a shared corner, and then see if we can figure out how to glue everything else together 3 to a vertex. And that's exactly what I did, right? So I did this process by hand on paper. I actually did this 10 years ago and then drew some diagrams on the computer 6 years ago in 2014 for that old Bridges talk. So, the details of the process, it'd take me a while to get them back, but the general idea is, well, look, over here you've got to glue some color in to be the third heptagon between A and C without loss of generality. Let's say it's Z. And then you start fiddling around. You'll notice that within the first cluster, we're going to have to glue A to D and B to C because they're not connected yet. So how do we do that? Well, maybe it's the most symmetric way, like this, and then, what the heck, symmetry. Do it the same way in the other one, and then you try and figure out what could possibly go here based on where Z is, and you try some stuff and it doesn't work, and the other thing doesn't work, and that thing doesn't work, and nothing works. So you go, okay, shoot, we were wrong about that. How about maybe we glue the opposite things not symmetrically like this, and then we probably have the same lean in the second cluster. If it doesn't work, we'll fix that too, but let's try that. And then what goes here? And you play around a little bit, and you find, oh, hey, this works, and then you can complete it, and you can figure out what that looks like in the other cluster, and voila, you have an arrangement that works. But what are we looking at here? Well, first of all, the ABCD cluster has 16 of its edges glued to the WXYZ cluster. Those are the edges labeled here. And they're labeled to reflect the fact that the remaining edges in this cluster are the edges that are connected between A and D and B and C, and those are glued together so that the cluster actually forms, well, basically a torus, except you've got this big, messy hole that is filled by the remaining 16 edges, and they're filled in this order. So it's goes this way, and then this is glued here, and it goes this way, and then this is glued here. So you've got these 16 edges that are going around your puncture, right? So for my paper, I drew a slightly simplified diagram because it doesn't really need to be in this heptagonal shape. To make it a little bit easier to see, I drew it like this so that you can see the punctured torus aspect of this a little bit better. Each one of these clusters is going to form a punctured torus, as shown by the arrows marked in here, right? So here you glue these together, you glue these together, and now you've got the corners fitting together to give you a big puncture that has the colors that we see on the outside around it. And so you can actually pull out that information from these two halves and show that what you're seeing at the puncture is the third diagram at the bottom there. And this is super useful because it turns out, first of all, that in practice, it's actually not that hard if you have these colors arranged in this way around a puncture in your torus to then fill in the rest to connect red to red and white to white and yellow to yellow and orange to orange. So you don't actually need to retain your diagram with the heptagons. You can just kind of fake that on your actual surface. And second of all, if you look at this boundary diagram, you can check that all of the color contacts we need are already there. So if you get this diagram going around the puncture, all you have to do is connect the colors up into single countries, and you have a map that's guaranteed to work. And that's exactly how I did this T-set, right? There's a circular boundary between the mug on the bottom and the teapot on the top. I divided that into 16 congruent segments. I made the color connections work the way they did on the diagram on the previous slide, and then I just connected everything in a way that flowed nicely around the T-set. So this is how I made T for 8 in 2010, which was then exhibited at the Joint Math Meetings exhibit in 2011. Now, during the same time, I was working on bead crochet bracelet designs with Sophie Sommer and Ellie Baker. In fact, we had put together a number of 7-color torus map designs because bead crochet bracelets naturally have toroidal surfaces. And so they're a nice vehicle for those sorts of designs. So in the next few years, Ellie and I did an extended research project on this. We wrote a book together, and I learned how to bead crochet myself. And in early 2014, I had this aha moment where I realized that there was a way to crochet not just a torus, but an actual double torus. And at that point, I had to apply this map scheme to that double torus. And so that process was very, very similar to the process for the tea set in that it started with, this is a bead crochet diagram that is just encapsulating that color junction diagram that was in the 2014 paper. And so I just started from this very basic diagram. I embellished it so that it would look more aesthetically appealing, rearranged this a little bit, filled in the rest of the pattern to connect the two punctured tori, and I ended up with this pendant, 8 color 8, which appeared in the art exhibit the year of that Old Bridges paper. And this eventually developed into a longer version of this that was long enough to wrap around a wrist and became part of this jewelry set that has an 8-color double torus bracelet, a 7-color torus pendant, and 2 flat 4-color earrings. But in the double torus bracelet, in the pendant, in the tea set, the heptagons were gone, right? I'd used that framework to get the information that I needed, and I'd completely thrown them away. And that's the way things stood until very recently, when I started playing around with these things in crochet. In particular, I went back to the original torus tiled with hexagons, because it occurred to me that crochet is perfect for crocheting regular hexagons. In fact, the most classic regular polygon in crochet is the granny square, which is a very quick way of crocheting up a square. And people had already adapted this into various forms of granny hexagons. If you sew 7 of these granny hexagons together, you get granny's torus. It gives you a really nice physical manipulable version of that 7-color torus map. Now, I'm not the only person to have done this. I'm not the first person to have done this. In fact, Moira Chaz has a very nice version with just some single crocheted hexagons. But having done this, I thought, well, wait a minute. There's nothing stopping me from crocheting heptagons. I wonder if it could work. And it felt a little crazy, and I didn't really think it could work, but it turns out it totally does. So to make these heptagons, I kind of fused together modules with the angles that I wanted. So there's one corner in each heptagon where four heptagons come together. So for that, you want a right angle, like this corner of this solid granny square. And at the rest of the corners, you're going to have 3 things coming together. So you want a 120-degree angle, like at the corner of this granny hexagon. And so I just fused these two together. So this upper left corner here, that's just a quarter of the solid granny square, and the rest of this is, excuse me, a granny hexagon with the square grafted into the middle of an edge. In fact, you can see this even more clearly if you see how I blocked these out. So this is the part of this process where you wet the crochet and then pin it to shape so that you get the angles and lengths that you want. The right degree angle has much more solid crochet around it, so blocking that wasn't so important. So I just kind of let that bunch up, and then you can see the rest of this is just this granny hexagon with the square corner grafted in right there. So if you make 8 of these and you glue them all together, you end up with Granny's double torus. So here you can see one of the 2 degree 4 vertices. We have 1, 2, 3, 4 faces around here, sort of the warm color faces. And if you flip this over, that's the other degree 4 vertex. So those are the cool color faces. And then here we have hole number 1 and hole number 2. And so one of the little surprises here is that the holes are roughly perpendicular to each other. So it kind of makes a nice, weird, angular muff. Now, if you want to see the other corners better, you can kind of flip this inside out in a number of different ways. And so if you do that, then you start to expose some of the degree 3 corners. 1, 2, 3. There are a few more over here. And so you can see sort of a bunch of the other connections. Of course, when it's turned around this way, you kind of lose the other hole a little bit because the openings are sort of tucked into the inside. So if you kind of twist it around in different ways, you can get the other hole to come out. Usually it doesn't take that long before you start seeing those right angle corners again, because they're sort of, prominent and visible. And so it's not that hard to re-straighten this out the way that it was when we started. Just to take a look at the color connections here, right? I'm not going to trace all of them, but if we look around white, you can see, for example, there's white connecting to yellow. Here's white connecting to blue and to orange, right along there, and then to black, and to green, to purple, and finally to red, and that brings us back to our right angle corner again. So there you go. Granny's double torus.